Welcome, everyone. Today, we are diving into a transformative topic, designing and implementing a machine learning operations, or MLOps, infrastructure. Let's get started. Let's begin by defining our core concept. Machine learning operations, or MLOps, is essentially the application of DevOps principles to machine learning. Why is this so critical? Historically, data scientists built models in silos, making it incredibly painful to push those models into real-world applications. An effective MLOps strategy solves this. It allows for the rapid creation, continuous update, and seamless deployment of models, all while ensuring that high quality is consistently maintained. Think of it as the bridge that connects the brilliant experimentation of data scientists with the rigorous, stable delivery standards of IT operations. Looking at this diagram, you can see the MLOps engine sitting right in the center. On the left, we have our data science team creating models, and our IT operations team focusing on security and scale. MLOps acts as the unifier. Instead of a manual handoff, the engine ingests these inputs and automatically routes them to the right, enabling continuous updates and powering our production applications with real-time, reliable endpoints. To build a robust and future-proof MLOps system, we must follow a high-level architecture broken down into 6 crucial stages. It starts with the setup of your Azure resources. Next is the inner loop model development, where data scientists iterate and train. When they are ready, we hit continuous integration, automatically packaging and registering that model. This triggers the outer loop, or model deployment, pushing the model to a testing endpoint. We then use continuous deployment to rigorously test and ultimately promote the model to our production environment. Finally, we never just walk away. We employ monitoring to track endpoint performance and model health indefinitely. This flowchart visualizes the continuous lifecycle. Notice how it flows from setup down through the inner loop of development, into CI/CD, and finally into monitoring. The most important detail here is the dotted line looping back from monitoring to model development. This represents the feedback loop. If monitoring detects performance drops, it automatically triggers the data science team to retrain the model, ensuring our system is always improving. When working with machine learning models at a large scale, deploying everything in a single workspace is a recipe for disaster. We must separate our workloads into dedicated environments: development, staging, and production. The development environment is strictly for the inner loop. This is where data scientists train models safely without accessing sensitive personal patient data. Once the model is registered, it moves to staging. Here, we run automated linting, unit testing, and endpoint deployment checks. Finally, only after rigorous testing and approval, the model is promoted to the production environment, where it is integrated with live applications to serve real users. Here we see the strict boundaries of our 3 environments. On the left, development contains exploration and training. As we cross the boundary into staging via packaging and registration, we shift to testing. Crucially, look at the transition from staging to production. It doesn't happen automatically. It requires a gated approval, ensuring a human in the loop verifies the model's safety and efficacy before it ever reaches the live web app. Let's talk about source control. In a professional MLOps setup, the golden rule is this: no one should ever be allowed to push changes directly to the main branch. Instead, we use feature-based development. When a data scientist wants to test a new hyperparameter, they create an isolated feature branch. Once their experimentation is successful, they open a pull request, or PR. This PR acts as a secure gateway. It makes the proposed changes visible to the team for discussion, and more importantly, it automatically triggers our CI/CD pipelines to run quality checks to verify the code. Only after these checks pass and manual approval is granted can the code merge into production. This Git graph perfectly illustrates the feature-based workflow. The solid line is our main branch, our production code. The data scientist branches off to the feature hyperparameters branch to safely make their commits, tuning rates, and testing scripts. Notice the merge point back to the main line. That merge only occurs after the PR is opened and all automated quality checks have successfully passed, guaranteeing production stability. To execute all this automation, we rely on GitHub Actions. GitHub Actions allow us to orchestrate our entire MLOps strategy by triggering workflows based on repository events, like a push or a pull request. But security is paramount. To let GitHub talk to Azure Machine Learning, we create a service principal. We absolutely never store these credentials in our code. Instead, we lock them down using GitHub secrets. Once authenticated, we define our workflows using YAML files, detailing the exact steps required to check out the code, sign into Azure, and trigger the remote machine learning training jobs on Azure Compute. Let's walk through this sequence. The data scientist initiates the process by opening a pull request in the GitHub repo. This event instantly wakes up GitHub Actions. Behind the scenes, GitHub Actions retrieves the encrypted Azure credentials, reaches out to Azure ML, authenticates, and submits the training job. Once Azure ML finishes training and registering the model, it reports back, marking the PR as successful and ready for human review. When our GitHub action triggers a training job, what happens inside Azure ML? This is where MLflow comes in. When experimenting, if we don't track our runs, we lose critical insights into which configurations yielded the best results. MLflow is an open-source library that logs every parameter, metric, and artifact associated with a model. We can enable auto-logging in our Python scripts, meaning MLflow automatically captures all this telemetry without us writing extensive custom logging code. More impressively, when we package and register the final model as an MLflow artifact, it enables no-code deployment. This means Azure ML can serve the model later without us having to manually write scoring scripts or build Docker environments. This diagram breaks down the MLflow tracking process. During the execution of the training script, the autolog command acts as a funnel. It automatically siphons off parameters like learning rates, performance metrics like accuracy, and the actual model file artifacts. All these disparate streams of data are pushed directly into the Azure ML model registry, creating a perfectly documented, version-controlled asset ready for deployment. Once our MLflow model is registered, we enter the outer loop, continuous deployment. The first major decision is how to serve the model. We can use batch endpoints for processing massive datasets overnight, or online endpoints for real-time, immediate predictions required by live applications. However, automated deployment doesn't mean blind deployment. Our GitHub Actions workflow includes gated approvals. Even if the staging deployment succeeds perfectly, the workflow halts. A lead data scientist or software engineer must manually review the metrics and staging performance. Only when this human-in-the-loop approves the deployment does the model get pushed to the live production endpoint. Observe the deployment journey here. The model leaves the registry and lands on the staging endpoint. Automated tests fire off immediately. If they fail, the pipeline halts. If they pass, we hit the crucial yellow diamond, the wait for human approval. Only upon explicit human sign-off is the model allowed to cross the boundary into the production endpoint, ensuring ultimate safety and reliability for end users. Let's tie all this together with a real-world use case. Consider Prosware, a healthcare startup that built a diabetes classification model. Their practitioners use a web app to input patient data and receive real-time disease probability scores. The challenge: medical data drifts. A model trained on one geographic population may degrade when applied to another. By implementing this MLOps infrastructure, Prosware's data scientists can securely analyze new regional data in their isolated dev environment. Through feature branching and GitHub Actions, they automatically trigger retraining. The new, highly accurate model flows through staging, receives approval, and seamlessly updates the live online endpoint. The web app never goes down, and practitioners continuously receive life-saving, accurate predictions. This final architecture summarizes Prosware's success. New regional patient data securely enters the dev environment for retraining. The GitHub Action CI/CD engine takes over, pushing the model to staging for health checks. Once approved, it updates the production online endpoint. The practitioner web app communicates back and forth with this endpoint in real time, providing immediate, drift-corrected diagnostic insights directly to the doctors.